Okay, guys, thank you very much for joining us today. We have Professor Gabriel Katul from the Nicholas School of Environment at Duke University. So Gabri is one of the most respected and cited scientists in atmospheric turbulence, and in particularly on the interaction between atmosphere and the biosphere. So it's very well known for his work on modeling vapor fluxes and CO2 fluxes, and in general, all interfaces processed between the atmosphere and soils, or between atmosphere and free water surface for flux exchange and gas exchange through lakes and oceans. So I'm very excited to have Gabi here, so the floor is yours, and thank you very much for being here.
Thanks for having me here. The work would actually be focused more on short crops and water rather than forests. This work is done in collaboration with my colleague, Heping Liu, from the Department of Civil and Environmental Engineering at Washington State University. The significance of turbulent exchanges near interfaces is not something that we need to preach about too much as to why we are studying this. But perhaps the problems in terms of human health, ecosystem, and climate-related processes is forcing us to think about ways to represent these complex exchanges in much simpler ways so that they can be used in conjunction with other scientific problems to make progress on them. And perhaps few examples that come to mind, or perhaps are iconic as to why to study these types of processes. One of them is the tragedy that has happened in Lake Nyos. This is a crater lake, so there's a lot of CO2 in the base of that lake that suddenly got degassed, and this massive degassing resulted in the deaths of more than 1,200 people. And what happened is that this degassing, of course, is a gas transfer process. Advection occurred and pushed this elevated CO2 into nearby villages, and it resulted in loss of life and crops and animals. In terms of climate processes, what also is interesting to track in the recent IPCC reports is the estimation of CO2 or in general carbon fluxes from inland waters, whether it be it lakes or peatlands. And the estimates that were provided by the IPCC report suggest that they are on the order of about 2 petagrams of carbon per year. Peatlands alone are producing methane that is on the order of 0.6 petagrams of carbon per year. And to put these estimates in some context, if one looks at the elevated atmospheric CO2 that has occurred between 2000 and 2006, the growth in CO2 has been something along the lines of 2 parts per million per year. And if you ask what would be the global source that would generate this sort of increase in atmospheric concentration, that would be about 4 petagrams of carbon per year. So just to give you an order of magnitude estimate as to the uncertainty that those numbers might be projecting vis-a-vis anthropogenic emissions. Last, perhaps in the air quality arena, gas transfer from interfaces is also receiving some attention. The nitrous oxides emissions from actually wastewater treatment plant, and as well as agricultural crops, especially because of fertilization, is also gaining some traction in the scientific literature. In fact, some journals now even called nitrous oxide as the new enemy of ozone. So while the significance of mass transport at these interfaces is perhaps not in dispute, the mechanisms of representing them, especially in terms of how to put the complex transport processes by turbulent eddies in those types of approaches that quantify mass transfer from these interfaces, remains multifaceted, and exactly that's what we are going to try to explore in this talk. Now, advances in measurements and simulations are almost ahead of theory. There is almost a renaissance in mass transfer studies at interfaces, and partly from the experimental side, there's been lots of developments in terms of infrared cameras now being able to sample almost at fluctuations of turbulent eddies that are on the order of 50 to 100 hertz. You have eddy sizes that are now almost resolved by infrared cameras that are on the order of millimeters. Fiber-optic cables is another development that are able to handle things at interfaces. So you stick a fiber-optic line and you could measure temperature fluctuations almost to within a few millimeters now. And stable isotopic techniques that are by no means new, but they are becoming cheaper and more readily available and much more accurate, are also paving the way in figuring out mass transfer coefficients. In terms of simulation worlds, the recent advances in computing, especially large eddy simulations and direct numerical simulations, is providing a wealth of results, but there are so much results that we don't yet have a clean organizing framework to understand them. And so what seems to be lagging, or sometimes even lacking, is some sort of a theoretical, even phenomenological framework to try to put all these results in some perspective that then can be used in large-scale models. So what is done in large-scale models, the focus there is on a quantity that is often referred to as gas transfer velocity. And so now I can, sorry about the low tech here. The gas transfer velocity K, and that's nothing but the flux out of this interface divided by some concentration difference that is often based on some surface concentration value and bulk concentration value. And the goal of this talk is to try to figure out how to bring eddies into the description of K, okay, turbulent eddies. That's the essence of where we're going to go with this talk. And this is by no means the first time such an attempt has been made. The current accounting of turbulent eddies, at least in a simplistic way, the accounting of turbulent eddies on the estimation of K has been based on what is called surface renewal schemes, which we will touch upon today. But the key outcome of these surface renewal schemes is that for an air-water interface, what is called water-side gas transfer velocity, that's what's coming out of the water basically, is assumed to be proportional to the Schmidt number to some exponent n multiplied by the water-side dissipation rate multiplied by the viscosity of water raised to some 1/4 power. This was derived by Lamond and Scott in a quite influential paper that is cited heavily in the oceanography literature. But 5 years ahead of the oceanographers, the civil engineers, I should add, and the hydrologists in particular, derived actually that equation. It was just not put exactly in that form. It was put in this form. And it was done by my great-grandfather, academic grandfather, Wilfrid Broussard in 1965, where he actually showed that K is proportional to the square root of the molecular diffusion coefficient multiplied by the so-called friction velocity that is related to the shear stress at the interface, raised to the 3/4 power, which is different from fully turbulent theories that would have assumed a linear exponent here, multiplied by the von Karman constant, the viscosity of the fluid, multiplied by Z0, the momentum roughness height of the surface, raised to the -1/4 power. So clearly there is a connection between these two, the -1/4 exponent and the 1/4 exponent here, which we will show in a minute. So what was interesting here is that in both formulations with surface renewal, or in the case of, again, surface renewal, but from rough surfaces rather than from water surfaces, is that the coefficient A and the coefficient alpha appear to be robust. So irrespective of the surface, it seems to be a fixed number. So that was somewhat surprising. So what we are going to show now is that these formulations, first and foremost, inherit their universal character from Kolmogorov's theory for turbulence. And we will show that the proposed derivation will show why these constants, alpha and A, are not so sensitive to the specifics of the interface, and why actually the whole machinery that has been developed in surface renewal is not sensitive to the distribution of contact times that is an important parameter in surface renewal. Okay, so to do that, let us just again recap and define the terms one more time. We're going to be focused on the gas transfer velocity on the water side. So when we focus on an air-water interface, we're going to assume an academic water surface here, meaning flat, no waves, no bubbles, no surfactants added to the surface, so everything is clean. We will assume that the concentration at the surface can be computed from the air concentration. So the water side concentration can be determined from the air concentration through either Henry's law or some solubility, Oswald solubility coefficient. We will assume that the concentration is going to reach some near constant value, not necessarily constant, but sufficiently less variable than the difference between this bulk concentration and the surface. And that may be attained if the flow here is fully developed, whereas, of course, the flow here may be intermittent when it comes to turbulence. And so the flux divided by this concentration difference, Cs minus Cb, defines the gas transfer velocity. OK, so this is the definition. Now, climate models basically try to estimate K using some easy-to-estimate metrics in the atmosphere primarily. And what is done in practice is something along these lines. K, the water-side gas transfer velocity, is assumed to be proportional to U, the velocity in the atmosphere, not in the water, yeah? The velocity in the atmosphere. And often it is selected at 10 meters height. Why 10 meters, if you are wondering? Many reasons. On the modeling side, 10 meters is the first grid node that the climate models use above the water interface in ocean models. And 10 meters also happen to be the size of the buoys that you stick on ocean ships when they're going out to sample. So if you have it vertical before you submerge, it's about 10 meters. OK, so K is A plus B U to the C in those models. U is, again, an air velocity. K is a water-side velocity. And if you look at the ranges of A, B, and C, C actually goes from 1 to 2, so anywhere from linear to quadratic. B varies by more than a factor of 3. And A is basically some sort of a bias. And if you're wondering how this came about, well, it came about from data sets that look like this. The x-axis shows wind speed. The y-axis shows the gas transfer velocity. Often you see a number here, 660. This is normalized to a specific Schmidt number so that you could do these experiments over multiple gases, but then reference them all to a single equivalent gas. Okay? And you see that for low wind speeds, there is not much variations in K. And as the wind speed increases, with some imagination, you could see that there may be two clusters of points, one where K varies quite dramatically, the other one K varies much more gently. And if you look deeper into the symbols and what is published here, you find that those that are in this interface happen to be for CO2, whereas those here happen to be more for dimethyl sulfide. And quite likely, those measurements are impacted by bubbles, air entrainment, and wave breaking, which will not be discussed here. But I should say one thing, that the models that do take those into account are always referenced to those models. In other words, you view this process as an enhancement process to some background value that is determined from states that bubbles and waves and air entrainment processes do not factor in. And basically, the reason this might be happening with the dimethyl sulfide is that there is no source or sink of dimethyl sulfide in the water. It's purely an entrainment process from the atmosphere, whereas a diffusive process from the atmosphere, whereas in the case of CO2, there is. So any bubble formation would have an impact on the gas transfer velocity. So for now, we're just going to be focused on this background state and leaving the other state for future research. So taking these fits into account, one then might go ahead and produce global maps of gas transfer velocity. And you see here a typical one. And you see ranges that go from 1.8 to 34.4 meters per day. These are global, these are annual averages, basically. And once you know the gas transfer velocity, then you could estimate from a global perspective how much inland waters may be contributing to the carbon budget, for example, of the atmosphere or other trace gases. So up to this point, you could say, well, the quantity that seems to be most responsible to for the transport, turbulent eddies, seems to be missing from those formulations. And that's what we're going to try to bring in. OK, so what has been done? This is already mentioned. Lamond and Scott in 1970, they published a paper that actually suggested the use of surface renewal and what they label in that paper as the micro-eddy theory that showed that K, this gas transfer velocity, is proportional to the Schmidt number to the minus n, dissipation rate, that's a water-side dissipation rate, viscosity to the 1/4. The alpha that they estimate was about 0.4, but the literature, there was quite a bit of scatter, anywhere from 0.2 to 0.6. The Schmidt number is the molecular Schmidt number, and that's often defined as the water viscosity divided by the diffusion coefficient of the gas in water. And this number is usually very small because the water molecules are so compacted, so to diffuse between them is not very easy, yeah, compared to air, which would be much easier. So the molecular diffusion coefficient of many gases in water is quite small. So that gives you a very high Schmidt number. This dissipation rate is known as the water-side mean turbulent kinetic energy dissipation rate. It is often very near the interface. And U is the viscosity of the water. The coefficient N here is often determined as 1/2. And as we shall see, surface renewal theory must estimate it as 1/2. They don't have any other choice. But actually, for wall-bounded flow, it'll be 2/3, just to show you that there is a difference. Yeah? Please. Yeah.
So what is the logic in using Kolmogorov velocity as a velocity
we're coming to that. That's the next step. So let's go ahead and just show what is it at first, and then we go why it pops up. Yeah. We will come to that in a minute. You're ahead of us. So basically, the meaning of this quantity, the dissipation rate, viscosity to the 1/4, comes about from Kolmogorov scaling of the finest eddies. So typically, the Kolmogorov length scale is viewed as the cube of the viscosity divided by the dissipation rate to the 1/4. And that's basically where the handshake happens between turbulent eddies and molecular processes, viscosity. Likewise, the Kolmogorov time scale can be formed from the same variables. And of course, the Kolmogorov velocity itself can be formed from the same variables, dissipation and viscosity. And if you want to really see that this is truly a handshake between molecular processes that are forming the viscosity and turbulent processes, you could define a microscale Reynolds number that would be exactly 1, based on the definition of this length scale and this velocity. So for those length scales, if you like, both are important, yeah? Molecular processes and turbulent processes, equally important. So what is the support for this argument? Well, so far we haven't yet derived it, but we will in a minute. What is the empirical support for this argument? Again, another paper by Christoph Zappa in 2007 that was published in Geophysical Research Letters. They showed that if you plot the estimation from surface renewal theory on the x-axis and the measured gas transfer velocity on the y-axis for many, many marine and aquatic systems, it seems that the model is able to capture the data reasonably, okay, with a coefficient of about 0.42 here. Now, the first question that comes to mind is operationally, before we go to theory, operationally, how do you go about estimating this dissipation rate? It's a little bit of an art because you are trying to usually use data sets of the measured dissipation rate near the interface, but you can never really get to that interface, realistically speaking. And so if you look at dissipation rate profiles, they seem to be kind of approaching a constant value, and whether they go to a constant value at the interface or not remains anyone's guess. But I should say that the 1/4 power is quite damping. In other words, if you're off by a factor of 2, your error is 17%. Okay, so on a log scale, that wouldn't even show up. So that's the saving phase, if you like, of this approach. Also, we haven't seen how this approach is actually operational. This is all still theory, yeah? Okay, so now we go to answer the question, why the Kolmogorov scale? To do that, I'm actually going to switch. I'm going to now go to the air side and rough interfaces, and I'm going to use Wilfried Broussard's approach to make the point as to how surface renewal schemes work and what goes into them. And basically, what Wilfried Broussard did in 1965 is he published a paper on bare soil evaporation. And I actually decided to put the abstract itself because it's only 4 sentences. So if you're a graduate student, you are lacking inspiration to write your own abstract. This is a good paper to read for the abstract. It's a long paper, but it's a good paper to read for the abstract. And it says that evaporation is analyzed as a phenomena of molecular diffusion from a large rough surface into random-lived internal scale turbulent eddies. Again, the internal scale here is assumed to be Kolmogorov scales. Okay? The model is based on the principles of similarity and stochastic renewal. It is shown that evaporation is proportional to the 0.75 power of the friction velocity and to the square root of molecular diffusivity. And the last sentence is that this is in agreement with available experimental data. Okay, so 4 sentences. Quite nice. Very succinct. That's what you should aim for. Okay, so how does surface renewal theory works? Now, I'm going to try to compress 11 pages of Wilfried Broussard's derivation into 2 slides. But I think it still captures the physics of that derivation. So what Wilfried did, not me, this is Wilfried, okay? What he did, he said, take a bare soil. The bare soil would have undulations like that. Get rid of them and replace them with a momentum roughness height and flatten the surface. At the interface, you're going to assume that there's a certain water vapor concentration at the surface, and that rapidly decreases as you go with height, because if the surface is vaporizing water, then the concentration is expected to be higher there. And then as you move away from this surface, the concentration becomes roughly flat. Now, of course, in theory, there will be another logarithmic correction to this description, but that's roughly what Wilfried assumed in 1965. He added the logarithmic correction in 1975, okay, so 10 years after. But for the illustration of the surface renewal, let's not worry too much about the variations beyond that point. And then what Wilfrid assumed is that parcels of air that emanate from this region will be having a concentration that is CB, the bulk concentration. Then a sweeping event occurs. These parcels arrive at the surface. They make contact with the surface. When they make contact with this flattened surface, the only way water molecules enter into these parcels of air is through molecular diffusion. Okay? No other mechanism. So the parcels of air sit on that interface for a while. How long? Say tau. They get enriched because there is an evaporation rate. So water molecules now are moving from the surface into those parcels of air. But after a time tau, there is an ejection event. So those parcels of air disappear, and then instantly they get renewed. Okay? So that's called continuous renewal. So there is a label for it. There is no lull period. Okay? So always something happens. And basically what happens is that the concentration goes up, goes up, goes up, and then when the ejection event happens, it goes back down, and then the same process keeps repeating itself. Now you could say, hey, wait a minute, at the point this doesn't make sense. I agree. But over an extensive area, there is always some renewal event happening. So that's why you could imagine this more of a representative of an extensive space rather than an instant in time. Yeah?
It actually makes sense completely. What else can be the molecular diffusion?
I know, that's the point.
It has to be the...
Exactly. The only thing is that if there are undulations, the contact area is not exactly the same.
The question is for how long that renewal takes place.
That's where the Kolmogorov scaling comes. So let's go through the physics itself. Let's go through the physics a little bit itself. Again, this is highly summarizing Broussard's derivation. How does it work? Well, exactly that evaporation rate, yeah, is given by a molecular diffusion process multiplied by a concentration gradient. Now the art is to select an estimate of this concentration gradient. And Broussard's derivation basically yields an estimate for dZdC as delta C divided by some diffusive front distance, okay, a molecular diffusive front distance that Wilfrid Broussard argues should be proportional to the molecular diffusion coefficient multiplied by the contact duration. The longer the parcel stays, the more water molecules diffuse into the air parcels, and that should be the correct distance to scale dC/dZ. If delta C, this concentration difference, is estimated as C surface minus C bulk, yeah, so the concentration at the surface minus the mean concentration bulk, and if it is assumed to be independent of time, then quite readily you see that the evaporation rate divided by this delta C, so you bring the delta C here, is in fact almost an event-based gas transfer velocity that varies with the contact duration. And that is given as square root of the molecular diffusion coefficient divided by the contact duration. Of course, this is only valid when parcels make contact with the surface, so tau is assumed to be bigger than 0. So now the challenge is, well, big deal. How do I get an average gas transfer velocity? Well, now we move from conservation of mass, basically, to a little bit of probability and art. So Broussard made the assumption that if the contact durations are exponentially distributed, and that's not the most standard model in surface renewal, but certainly a viable one. It's a very convenient one because exponential distributions have only one quantity. And then he made the crucial assumption that the distribution of these contact times is not only exponentials, their mean value is the Kolmogorov timescale. The reason Broussard gives in this paper is that this is a process that is inherently molecular, so it must be the finest scales of turbulence that are actually lifting the water molecules from the interface into the bulk fluids. So his argument is that that will be therefore the mean contact duration. That's what he made as an argument, okay? So if you do that, then the mean contact duration becomes the Kolmogorov timescale, and then the rest becomes pretty standard algebra. You integrate over all possible taus based on this PDF, and if you do the integration with some algebra, you get k to be proportional to the Kolmogorov timescale, well, somewhat related to the Kolmogorov timescale, but then with some adjustments, you get the Kolmogorov velocity appearing from this derivation. So the assumption is that while the contact durations do vary from a distribution, their mean is given as the smallest eddy that can penetrate this interface and move, basically, material from the interface into the other lived eddies. So that's the conceptual argument. Now the reason, if you do that, you get basically the same result as Lamont and Scott. Broussard did not put it on those terms. This is kind of a reinterpretation of Wilfrid's work. Wilfrid Broussard was a graduate of irrigation science at University of California, Davis. In 1965, he just started his position at Cornell University as a professor in civil engineering, but he really wanted his result to be usable as quickly as possible. So early on in the derivation, he made an assumption also that the dissipation rate is balanced by mechanical production, which would be u star squared du dz, where du dz is the mean velocity gradient. And he estimated du dz based on classical rough wall boundary layer theory to be u star divided by kv z naught, where z naught is the momentum roughness height. So with this condition, you could see that you could get rid of the dissipation rate here. And if you do that with a little bit of algebra, you get the usual result, which explains why u star to the 3/4 emerges rather than u star to the 1, and why z naught u kv to the -1/4 pops up. I should say that if you repeat this exercise with different assumptions about the contact durations, and I've done this myself to convince myself this is true. I've assumed Pareto distribution, power laws, gamma, walled, and log normal. Okay? And by and large, the shape of that distribution turns out to be less relevant. And what is much more relevant is the assumption about the mean contact time. That seems to be much more dominant than the precise shapes of the contact durations. Now, one more calculation with Wilfrid's approach, and then we will jump to the new things. This is just to show you what has been done using the two standard theories for surface renewal. You could also calculate what would be the diffusion distance, yeah? How long did these water molecules, yeah, move in the parcels of air? And that would simply be the random distance that we have been dealing with, which is based on the contact duration and the molecular diffusion coefficient, multiplied by all possible values of tau that is coming from the exponential distribution. And again, if you assume the same distribution with the mean duration to be the Kolmogorov timescale, you calculate this quantity, and it turns out to be the Schmidt number to the -1/2 multiplied by the Kolmogorov length scale. And that's nothing but the Batchelor length scale. Okay? So surface renewal theories virtually have to predict an SC to the -1/2 because of this argument. And of course, in air, the Schmidt number is not too different from 1. Yeah, you know, air molecules are so separated from each other that a gas molecule can move freely between them. So that's not a big issue. But in water, that's not the case. Okay, so just one more comment, since we have been discussing the scaling exponent. Is there any evidence for the -1/2 scaling? And the answer is yes. This is a paper by Takakagi in 2016. Takakagi plotted what is a normalized gas transfer velocity, with the normalization being the Kolmogorov velocity, so k over the Kolmogorov velocity, as a function of the Schmidt number. And for almost 3 decades, you see that there is a -1/2 scaling that appears to be valid. So the -1/2 seems to be supported by data. Okay, so this is the state in a kind of nutshell of what has been done to bring eddies into the description of K. Can we do something better? Can we actually bring aspects of the Navier-Stokes equations, turbulence, into the picture? Okay, so that's what we're going to do next. Can we make more contact with Navier-Stokes, not just contact durations? And to do that, we're going to reinterpret, basically, the gas transfer velocity in a slightly different way. Rather than think about parcels of air making contact, staying at the surface for a while, and then ejected, we could think of eddies actually bringing parcels of air down to the surface and bringing, again, parcels of air from the surface up to the region. And that means that if we can figure out how fast these eddies spin and what is their effective diameter that is responsible for the transport, we may actually be able to bring Navier-Stokes turbulence much more into the picture than surface renewal. And to do that, you could argue that the difference in downdrafts and updrafts generates for us a velocity difference whose root mean square value is nothing but the square root of the structure function. If you accept this as a phenomenological description of the gas transfer velocity, then you have a gas transfer velocity that is no longer represented with contact durations, but it is represented with a scale. Okay, so now we are moving away from an instantaneous gas transfer velocity that averages over a contact duration to a turnover velocity that is scale dependent. And the reason this is making more appeal to Navier-Stokes turbulence is that we have in turbulence theories lots and lots of theories on this quantity. So this is a mature field in turbulence that we can draw upon for this problem. So just to illustrate, what happens if we simply assume that structure function is purely Kolmogorovian, based on locally homogeneous and isotropic turbulence theories with no viscous dissipation corrections and no adjustments from large scales? What happens if turbulence is purely inertial? Yeah? The structure function is given by the Kolmogorov constant, the dissipation rate to the 2/3, multiplied by the separation distance, or eddy sizes here, interpreted as eddy sizes, raised to the 2/3. Notice that here there is no more contact time, there is just a scale. Yeah? And in fact, the arguments that could be brought upon have nothing to do anymore with the microscale properties. Yeah? They come a little bit later. So we interpret k to be simply the square root of that structure function. And if you make the same assumption that we have done with surface renewal, that the most effective eddy, just to see if we can recover the same results, yeah? The most effective eddy is the Kolmogorov length scale multiplied by the Schmidt number to the -1/2 in this structure function, which incidentally is wrong at those scales. Yeah? It's a very different result at those scales. That's not what happens at those scales. But even if you do that, you plug it in, and for a near unity Schmidt number, which is the case in the atmosphere, R becomes comparable to the Kolmogorov length scale. You plug this back in here, and you do a little bit of algebra, and of course you recover the Kolmogorov velocity. So at least there is some self-consistency in the formulations. I should also say that Broussard brought in his paper up a nice point, and this is again recasting it in this framework, that the Batchelor length scale must be much, much less than Z0 to ensure that the surface is rough, which is an interesting constraint on the roughness, on the scalar roughness height. Okay. But now let's move to the more exciting picture, which is the water. In the case of the water, we can still imagine the same phenomena happening. We interpret the gas transfer velocity as some sort of a spinning velocity with a characteristic scale that is given by the Batchelor length scale. The problem that we have now is that the cumulative energy, which is what the structure function contains, is deviating appreciably from Kolmogorov scaling in this regime. So we need to figure out a way to describe the shape of the structure function, yeah, in the not inertial only, but also in the regime where viscosity plays a major role. And do we have a theory that is based on Navier-Stokes turbulence that does that for us? Yes, it's called the von Karman-Haworth equation. Before we go through it, I just wanted to make a point that the experiments that have reported spectra, yeah, especially spectra for velocities near the interface, seem to support the view that there is some sort of a Kolmogorov scaling with a strong exponential or some sort of a cutoff. It's not exactly exponential based on these theories, but close enough. Okay, so what is the von Karman-Haworth equation? This is purely derived from Navier-Stokes for locally homogeneous and isotropic turbulence. It has 3 terms. It has a vortex stretching term given by the so-called third-order structure function. It has a viscous diffusion term, which is the gradient of the second-order structure function with respect to scale. And then it has an energy transfer term. And basically what you're saying is that as the energy cascades down scales, yeah, at a given scale, it's being carried by 2 processes, vortex stretching and viscous diffusion. As the scale becomes smaller and smaller, viscous diffusion becomes more dominant over vortex stretching. However, in the event that viscous diffusion is quite small, you have an analytic expression for the third-order structure function, which is given as the -4/5 dissipation rate times scale, which is the only analytical result that we have in turbulence, the only one. Okay? But this is unclosed because it simply relates a third-order structure function to a second-order structure function, so we need a closure. And the closure here for the vortex stretching term is some link between the third-order structure function and the second-order structure function. It is shown here with aspect of it given by Kolmogorov scaling, aspect of it is not. So this deviates a little bit from a well-established theory by Abukov in 1946 that was called the constant skewness hypothesis. It's not exactly constant skewness. It allows the skewness to evolve with scale. You take that expression, you plug it into the von Karman-Haworth equation, and after some algebra, you could show that the vertical velocity structure function normalized by its Kolmogorov value is nothing but 1 minus an argument here multiplied by the Dawson function of that argument. And the Dawson function is basically a function that looks like a bump, asymmetric bump function, if you want. The argument itself includes the usual suspects, the scale and the Kolmogorov length scale. More important is that in that argument, the Kolmogorov coefficient, yeah, appears explicitly, the Kolmogorov constant. Now, If that argument is small, so we are dealing now with length scales that are comparable to the Batchelor length scale that are much smaller than the Kolmogorov length scale, then what you could do is expand the Dawson function into two terms, a linear and the cubic, and say this is good enough. So with this two-term expansion of the Dawson function for small scales, you plug it back and do the algebra, and you could show now analytically that the gas transfer velocity is square root of 2 over 15, constant, doesn't depend on anything. Kind of nice. Schmidt number to the -1/2 multiplied by the Kolmogorov velocity. Numerically, square root of 2 over 15 turns out to be 0.36. And that's fairly close to Zappa's 0.41. So promising. Not yet fully there, but promising. So since it was promising, we decided to push more and see what other things can be recovered from it. In terms of measurements, one of the popular approaches that is used in determining gas transfer velocity is known as the surface divergence method. This was proposed by Banerjee in 2004. And what Banerjee did is he said, OK, if I have a flotation device, such as the one here, I can measure the fluctuations in this flotation device very accurately. So I can measure basically the vertical velocity at the surface. If I can put a PIV system and measure the vertical velocity just under this flotation device, I can determine the velocity gradient, dWdz. Well, dWdz is nothing but du dx plus dv dy in terms of incompressible flow, right? So continuity equation. Or as the graduate students often like to call it, incomprehensible flow rather than incompressible flow. So, one of those. Because in incompressible flows, you get lots of stuff, like stuff can move faster than the speed of light. OK, so under those conditions, you could show that K is Sc to the -1/2 multiplied by the square root of the viscosity times the surface divergence term. If you start with the result that we have just obtained from the structure function approach, and note that the dissipation rate can be inferred from the velocity gradient by the usual isotropic turbulence relations, 15 times the viscosity times dWdz squared average, you plug that back in here, and you do a little bit of algebra, you find that K, the gas transfer velocity, is a constant whose numerical value is predetermined, Sc to the -1/2 multiplied by the surface divergence term. And it turns out that constant is square root of 2 over 15 to the 1/4. You evaluate it, and you find that based on our higher order math here, it turns out to be 0.71, which is close to the value that is often reported from measurements and DNS results. The range is between 0.57 and 0.71. So again, suggesting that there is a close correspondence between the coefficient that is derived here and other ad hoc coefficients that have been derived from similarity arguments. So this is the addition over surface renewal, is that the coefficient now is predicted theoretically, or phenomenologically, I guess. Last check that one can do is what happens when you have convective cases. And under those conditions, you could argue that the dissipation rate is no longer just mechanical, but it has to do also with buoyancy. So you have to add basically the buoyancy production or destruction of turbulent kinetic energy explicitly. And in textbooks, you might see this as u star squared du dz, which is the mechanical production term adjusted by some sort of a flux-Richardson number that is defined as the buoyancy production or destruction divided by the mechanical production. And that Richardson is the same Richardson that is perhaps credited for the most famous poem in turbulence. Has to do with the big worlds and little worlds and viscosity. Yeah, that same Richardson. And in fact, what can tell you a little bit more about Richardson, then we jump to the final result. Richardson, in fact, was a Quaker. He was a conscientious objector during World War I, and so he refused to join the military and the war effort. And so he was penalized by having to serve in the medical unit. So if you had any doubts about his decision not to become a soldier, serving in the medical unit during World War I probably convinced him he did the right decision. But because he didn't serve in the army, he was precluded from holding any academic position, in fact. So he never held a position in the United Kingdom at all. So the only thing that he was able to get is to become the head of the UK Met Office, where, in fact, parallel computing, the ideas of parallel computing started. And in fact, Richardson also was studying quite a bit dispersion in the atmosphere. And there is the Richardson law, of course, also attributed to him. And later on, he discovered that the Royal Air Force was using his results to derive basically tactics to throw chlorine bombs on trenches. And so when he learned that, he actually burned all his notes. So we have no clue what gems, and many gems perhaps, were burned away by this decision. And after that, in fact, Richardson started moving to the studies of dynamical systems, particularly focusing on the calculus of war. How do nations enter war? What are the methods that could be used to prevent actually nations from going into war? So the studies about the calculus of war, I was arguing that the border between nations plays a role and so forth, and came up with the first set of dynamical equations that dictate under what conditions two nations go to war and not. And he was accusing the political establishment at the time that they were making decisions about war in a haphazard way based on basically witty comments. So he spent the remaining scientific career producing a book about the calculus of war. Anyway, so this is the same Richardson. Okay, so if we take the free convection limit now, with Richardson number going to infinity, basically, so you get the dissipation rate only due to convection, you find that K becomes square root of 2 over 15, Schmidt number to the minus 1/2, and then the buoyancy contribution to the TKE dissipation or production multiplied by nu to the 1/4. Now, the reason I'm putting this expression is that the numerical value, of course, is square root of 2 over 15, and quite recently, very high resolution direct numerical simulation by Fredrickson in 2016 estimated this coefficient under free convection condition to be 0.39, which is, again, quite close to the 0.36. Okay, so at this point, if you think that the problem is closed, it's time to readjust your optics. Certainly not. And it goes back to the question that was posed. Why the Kolmogorov scale? In the micro-eddy model, everything is related to the Kolmogorov timescale. In the case of surface renewal, in the case of the structure function, it's the Batchelor length scale. But the two are pretty much linked intimately. One could argue that, hey, wait a minute, rather than use the contact time to be Kolmogorov timescale, can we use something that is a little bit more macroscopic? Can we use a velocity that is more related perhaps to the turbulent kinetic energy of the flow, and a length scale that is more related to the integral length scale of the flow? So the combination of these two could form an inverse timescale, very much like the Kolmogorov timescale there. And you could define a Reynolds number that is based on that velocity and the integral length scale adjusted by the viscosity. And if you have high turbulent flows, this coefficient is much bigger than 1. This Reynolds number is much bigger than 1. And if you make the assumption that the dissipation scales with the cube of this velocity divided by the length scale, you take that expression, you plug it here, you estimate basically the ratio of the integral length scale of the flow to the Kolmogorov length scale, and you get the usual results that you see in turbulence textbooks, that the large scale is related to the Kolmogorov length scale with a Reynolds number that is raised to the 3/4. Okay, so this is fairly standard textbook turbulence. If you take that result, plug it back in here, and you do a little bit of algebra, you find that the macro-eddy model for K, that is based on these arguments, can be related to the micro-eddy model, shown here that we have just discussed. With one thing, this coefficient alpha becomes dependent on the Reynolds number to the minus 1/4. So this actually brings in contributions now from rod scales. So still the basic engine of the model calculations is this. Doesn't change with those arguments. What is changing, in fact, is that alpha now becomes dependent on some macroscopic property, basically the turbulent Reynolds number. So what do experiments and simulations say? Let's start first with the direct numerical simulations. These are taken from a recent paper by Herlina and Wissink in 2014. They actually showed that, yes, the gas transfer velocity in their simulation setup and experiments as well is correct, but the adjustment factor to it scales with the Reynolds number to the minus 1/2. And because these were DNS, they could not go for very high Reynolds numbers, so the Reynolds number is less than 500. And in fact, they point out that these simulations are consistent from experiments done in the mid-70s by Theophanos in 1976, where K was shown to scale with the microscale, basically gas transfer velocities, but there were different scaling with Reynolds numbers. So at RET less than 500, it seems that the scaling is more consistent with an exponent of minus 1/2, whereas for high Reynolds number, the exponent actually goes as minus 1/4, which is consistent with the argument that we have just shown. So if the Reynolds number is sufficiently developed, it seems that alpha does scale with minus 1/4 of the Reynolds number, but for lower Reynolds number, it seems to scale as minus 1/2. Okay, you could say, fine, this is all good and dandy. What can we say? It's easy to correct and the microscale model with some macroscopic Reynolds number. The problem is this, that the field data sets that have been collected thus far, when you plot them as a correction alpha here on the y-axis and the Reynolds number, some bulk Reynolds number on the x-axis, the data seem to suggest almost opposite trends. In this case, as the Reynolds number increases, alpha drops. It seems that some of this field data alpha increases. Now, one should be extremely cautious with interpreting field data like this because there could be a correlation between RET and alpha. Okay, so this is not to be excluded easily. I don't have the raw data, so I cannot repeat what they have done. However, it is worth pointing out that there seems to be inconsistencies between DNS and lab experiments and what is coming out from many field experiments when they're all thrown and lumped together. The value that we have just predicted from the von Karman-Haworth equation is square root over 215, and it is sitting somewhere here. So clearly much more work to be done to figure out how to bring in the large scales and why field data seem to be deviating from DNS and experiments. Okay, to finish, we started this whole talk by trying to figure out what the gas transfer velocity K is, and we wrote it as almost like a resistance law or some effective drag or whatever you want to call these types of relations that link flux to gradients. So it's almost like a macroscopic law. We came out with another expression for K based on the cumulative energy in turbulent eddies. Yeah? The structure function actually measures nothing but cumulative energy in eddies as a function of size. And we showed that through some arguments there is a certain effective size that allows us to recover most of the formulations that we have done before. When you equate these two, you are almost linking something that looks like a drag or a resistance to something that looks like an energy with a correlation length scale, R in this case. And that is almost, this we will not put in papers. This is, of course, just for talks. Quite seductive analogy to think of it as an almost fluctuation-dissipation theorem from statistical mechanics. And that analogy might open up ideas from statistical mechanics to be used in tackling gas transfer velocities. So the fluctuation-dissipation theorem links the drag coefficient in molecular motion, the drag coefficient with the energy content of the bombardments, the global temperature, and the correlation length scale of the fluctuations. And so basically the idea is that friction and fluctuation go hand in hand. Yeah? They both exist, and one can affect the other. So there is almost an exact analog. If you think about eddies as kind of the microscopic version, these are the building blocks of turbulence rather than molecules, and K being something like a drag coefficient. So the analogy is quite close. Okay, so with that, I'll end by noting that the famous statistician who spent some time at North Carolina State University, George Box, of the famous Box and Jenkins, had an important quotation. It's called, "All models are wrong, but some are useful." Hopefully this was one of them. Thanks.
Thank you very much. That was very inspiring, and a lot of material for our discussion and our study in the next weeks at least. Any question? Because Mickey, then John.
Very nice talk.
Thank
you. I have a question. Mass transfer velocity is an estimated quantity. You don't measure mass transfer.
Always.
It is an estimate.
It's a computed quantity,
yes,
for sure.
Energy dissipation that you use to scale the velocity is an estimate. It is not something you measure velocities and estimate it. But why don't you focus more on more fundamental ingredient in mass transfer velocity that will be diffusive sublayer thickness? Because mass transfer is diffusion coefficient molecular over diffusive sublayer thickness. And diffusive sublayer thickness we can
detect,
estimate from the concentration profiles. And the reason I'm asking this because your title is universal scaling. I think you can universally scale what you measure, and that would be concentration profile. And you can derive a power law expression from concentration profile. You can estimate directly diffusive sublayer thickness. So other attempts to
Link the
focus
two
more
on the diffusive.
on diffusive sublayer thickness?
It's an important point because basically the diffusive sublayer thickness in surface renewals, at least, is directly linked to the Batchelor length scale. And so now, if you infer K through some method, you certainly can use these expressions also to infer the effective sublayer thickness. And people have done that. It's not, so it's done. And in fact, not just measurements, I mean, this is even more of a point because with fiber optic cables, if you are able to shrink the fiber optic line to very tiny numbers, you could actually even measure temperature profiles at enormous resolutions. So there is a lot of information that is coming that we never had before. I mean, we never had temperatures every 0.005 millimeters.
Normally we use temperature fluctuation to estimate dissipation
Right.
through the Batchelor spectrum.
Right.
And rather than velocities that
Right.
these scales
Right.
are very difficult to
Right.
measure.
I totally agree. It was basically trying to show that there may be a different interpretation for the gas transfer velocity that is more linked to a turnover velocity. The Batchelor length scale pops up as an effective eddy size in this case rather than effective thickness, but it's the same argument. It's basically the same thing. Point well taken.
Hi, thank you for the talk. I get two interesting things out of your talk. The first is that I believe that you feel that Broussard developed the small eddy model.
No. This was developed by Higby in 1930, but Broussard put it in the context of
Well, I
evaporation.
mean the Lamont and Scott version of the small eddy model.
Yeah, well, before them, yeah.
Right. Secondly, I feel that you're not giving credit to Danckwerts, who developed the surface
Danckwerts,
renewal model.
actually Broussard cite Danckwerts. The whole exponential
Yeah.
PDF is all Danckwerts. This was all taken from Danckwerts' paper, where actually he revised Higby. Higby was uniform distribution, Danckwerts was the exponential distribution.
It's interesting, the Lamont and Scott, the history of the Lamont and Scott model, because Lamont and Scott developed it, published the work in 1970. Banerjee says that he and Scott developed it in 1968, has a publication, and now you tell us that Broussard has a publication.
In 1965.
So the timeline is kind of moving back.
I'm sure somebody has looked at this before Broussard. It was just public. It was so visible in Broussard's book on evaporation that this paper never really received the attention that it would have received. and I think if Broussard did put it in the form that was at the end presented by Lamont and Scott, which would have been
Yes.
this form.
Yeah.
Oh, sorry. Would have been this form rather than this form, it might have actually gained more traction. Broussard was very much interested in having surface renewal of Higby and Danckwerts used in evaporation modeling for real-world agricultural application. That was what was driving his research. And he, early on in the derivation, got rid of the dissipation rate and put it like that. So all the end result was this. And this is also iffy. du dz being u star over kvz naught. He's extrapolating the log law almost down to the roughness sublayer, which is, there are corrections to that.
Of course, surface renewal is a conceptual model, and that it's not based upon Newton's second law of physics. So it just came out of somebody's mind, right?
It is.
You tried to relate it to the Navier-Stokes equation, and you made an assumption in your talk that I didn't quite understand. Can you go back to that assumption to make the connection between the surface renewal model and the assumption was a distribution?
The assumption was to revise the conceptual thinking of surface renewal from contact times, get rid of that, and think about the gas transfer velocity as a turnover.
Yeah, could you go a
Turnover
couple slides
velocity.
Could you go a couple slides farther? I'll talk about the part I didn't understand. No. You're going back or forwards?
Back.
I'm talking about forwards.
Oh.
Sorry. No. No. Next one.
That's it.
That's it. I must have forgotten. Let's go back one. Let's go back one. Not four. Go back one. So, no. There was a distribution the connection between the Navier-Stokes equation and the small eddy model was made, but you made an assumption about a distribution of eddies that I didn't quite understand.
Right. Actually, it is here. And that was Danckwert's argument, in fact. It was an exponential distribution. So Danckwert's original paper said Higby made the assumption of uniform distribution. That's not realistic. An exponential distribution would allow some imbalance in terms of contribution of big eddies or longer contact times and smaller contact times. So that was the assumption. The connection to Kolmogorov scaling is when you assume that the mean contact time is given by the Kolmogorov timescale. So that's really the only mechanistic link that then allows you to take the contact durations and convert them to something usable.
Okay.
So the only physics in it is what is the mean contact duration. Now, I should say that since Higby and Danckwerts and many others worked on surface renewal, there are many complicated surface renewal schemes that have dead periods where nothing happens, where in fact the concentration difference that we have assumed, this delta C, is no longer independent of time because, in fact, when eddies make contact with the interface, if you don't have, in the case of temperature, let's say, if you don't have low thermal inertia, if you have low thermal inertia, in fact, these eddies bombarding the surface can change the surface value. So there is more interaction between the eddies and the surface value. In the case of oceanography and maybe water, not a big deal, but in the case of vegetation that has very low thermal inertia, it could be a big deal.
Okay, I think we should talk about it later, but
Yeah.
thank you.
You have a slot. I have one tiny question before we have to stop. When you consider the connection between the macro eddy and the micro eddies, is it possible that the macro eddies are locked in size by the formation of little waves? And that may explain
The waves?
waves at the interface. And that may explain why perhaps if simulation, assuming a flat surface versus experiments where there might be little
Wavy
waves
surfaces.
is
I mean,
critical.
the waves could play a role, and in fact, Xanadi already did this. So you could show that the end result would bring you with a variable that would have a timescale that is dependent on U star, the gravitational constant, and the viscosity. And but I think those were still, yeah, maybe. I mean, I don't know.
I'm talking about gentle waves where
Right,
they will
right,
lock
right.
the
Yeah,
the size
the vortices,
of
the vortices
yeah,
itself are
and they
locked.
kind of mix
And
away.
those waves end up also reflecting upwelling and downwelling of eddies from the base.
Yeah.
So yes, they could. Because they were field data, so I'm sure there is some
Yeah,
waviness.
there
Yeah,
has to be something, right?
yeah.
Okay, one more tiny. Very. Okay, you're gonna meet Liam. So thank you very much. That was.